Welcome everyone. So today we are going to talk about manifolds. In our last class, we discussed topology and the continuity of the functions and all those stuff. So today we are going to start with manifold. But before I begin, let us quickly review what do we mean by homeomorphism and when two topological spaces are homeomorphic to each other. So if I have a topological space M, O, M, and N, O, N, so okay, so how do I know these two topological spaces are homeomorphic? Only bijective map? Okay, so I need a map from M to N. This F, it has to be continuous. And since it is a bijective map, I know there exists a inverse of this map, F, and this F from N to M is also continuous. So then I can say these two topological spaces, MOM and NON, they are homeomorphic to each other. Now, so today we are gonna focus on some special type of topological spaces, which is something related to the intuitively the surface of the earth. How do I see the surface of the earth? So in general, the earth is a sphere, but locally it is flat, right? So this spatial type of, okay. So this spatial type of topological spaces are actually, we are going to define as the manifold. So to do this, let us start with the definition. Manifold. A topological space manifold of dimension n is a Hausdorff second countable locally Euclidean space of dimension n. Okay, so there are a few terminology here. The first one is Hausdorff, then second countable, then local Euclidean. So what do we mean by Hausdorffness of a topological space? Right. So it is the T2 separability condition, which is if you take 2 points, P is not Q, belongs to the topological space M, then you can always construct an open set around this. Let's say this is P and this is Q, and these two neighborhood, they does not intersect. Okay. And for second countability, we are not going to consider this. In our context, it is not very important. But for local Euclidean, so this is very important. What do you mean by local Euclidean? So say I take a subset U of the set X. U is open if U belongs to OM. So if U, the set U belongs to the topology, then it is open. Now, how do I construct, or how do I relate this U with the Euclidean space? Or if there exists a homeomorphism with this U to any Rn, then homeomorphism phi from U to Rn, then we say definitely this should be phi of U, which is a subset of Rn. Then we say U is homeomorphic to a subset of Rn. And this is the locally Euclidean condition. Okay, so and if I can do this for all the points in P, so for all P, if P belongs to U and we have phi I, then we say if Euclidean. So if I have this phi I with this set ui, let's say, then we say this topological space M is a manifold. Okay. So, so let us consider some example. So start with R with the standard topology. So is it a topological manifold? Can I construct a homeomorphism from this R to some Rn? What will be the homeomorphism? The identity map, and the set is the R itself. So there is a global chart set, right? So although I didn't define what a chart is. So this is a topological manifold. Also, I can consider example of something like this. So this is an equation of the form e to the x to the 2/3. So first of all is this set given by this equation y equals to x to the 2/3. Is it a topological space? It is, right? I can induce the subspace topology of R to to this. Now, is it a topological manifold? Is it? It is, right? Because the so I can consider x comma x to the 2/3, the graph, and if I project it to the first component x for every points, right? So hence it is also a topological manifold. But what about this? Say I have something like this. Is it going to be a topological manifold? For this point, there is no problem. Even in this case, there is no problem. In this side, there is no problem. But the only problem is with this point. I cannot construct a bijective map to some array if I take the neighborhood around this point. Yeah. No. Okay. So these are the examples of topological manifolds. Now let us consider few terminology. So first one is u comma phi is a chart on M, and then an atlas A equals to, so u alpha comma phi alpha is a collection of charts such that union of alpha u alpha is equal to that. And finally, the map phi of p is equals to phi 1 of p up to phi n of p, where p belongs to M, are called the coordinate maps. So this is kind of a bit abstract, but let us think about it. So we know an example of the atlas, which is basically the atlas of our Earth, right? So phi is the homeomorphism. Since I'm considering phi from U is a subset of M to some subset of Rn, that means this phi maps, if you feed a p points to this phi map, then you get n tuple of, yeah, right, yeah. Yeah. So basically, P is a point in the manifold, but what do we mean by a point on the manifold? So let's say I have a point. So this is a point on the Earth, right? But how do I see it, or how do I model this point to do mathematics? To some Rn, right? So if I map this point P to some Rn, then I get what? Oh, those phi ones are basically mapped from M to Rn, the real numbers. Because Rn is what? R cross, right? So it is a n-fold Cartesian product of real numbers. So essentially, these phi ones, they are mapped from the manifold to the real numbers. Where I'm saying that? No, there is a comma, you see? The map phi of P, where P belongs to M, are called the coordinate maps. So basically, a bit more specific if I write something like this. Okay, so like if I consider the atlas of this Earth, so this will be something like collections of pages, right? And I know different pages have different maps for different places. So now, what is we are interested about is, say, this is my manifold, and there is this set U, and there is this another set V, and this U intersection V, it is not empty. Now, for this set U, I know there exists a homeomorphism. That means I can map this U to some phi U, phi. So this is phi U, and also I can map this thing by phi prime. This is going to be something like, let's say, phi of V, phi prime of V. But yeah, right. Yes. Okay, so since these phi and phi primes, they are homeomorphism, so I know there exists a invertible maps. So let us consider this part of phi of U is actually phi of U intersection V, and this part phi prime of U intersection V. Now I can define a map from here to here, because for the phi, I know there exists a phi inverse, and also for phi prime, there exists a phi prime inverse, right? So if I take a point here, then I can define, so this is basically some RD, Rn to this is some other Rn. Then I can define a map from Rn to Rn. And what will be the definition of this map? So I need to go to this direction, then here too. So that means I have to apply phi inverse, then phi prime. Right? So this is a nice construction because so this is basically give us the idea of continuity again, because I know composition of continuous functions are what? Continuous, right? If I take the composition of two continuous functions, then the map is again a continuous function. Okay. So that means the topology on the manifold M give us this some kind of a transition map from one coordinate system to another coordinate system, right? So, and formally I can write it like U intersection V phi and phi prime. So this is phi of U intersection V, phi prime of U intersection V, and this is phi prime of phi inverse. And this map it is called the chart transition. Okay, so why do I need chart transition map? So we need chart transition map because this is a chart, this is another chart, but possibly there is an intersection. Sorry. Possibly there is an intersection of a common place, right? So I need to know how I can go directly from one coordinate system to another coordinate system, and so that the result doesn't change from one place to another. Okay, so so far the structure we have, this guarantees are something like this. So let us consider R from to U, which is a subset of F. I can always consider curve as a function from the real number set to the manifold. So this will be something like a gamma. And let's say I have a map phi here, then this is phi of U. And let us consider this is just is a subset of Rn. So this function phi of gamma, it is a map from the real number set to the R again, right? R to Rn. So if this function is continuous, then I can definitely have a different coordinate chart here, phi prime, and this is phi prime of U, and then it will be phi prime of gamma. So if this one is continuous, can I say this is also continuous? If this phi of gamma is continuous, can I say this phi prime of gamma it is also continuous? Yeah. Generally, yes, because we already have topological structure. Because I can write phi prime of gamma by phi prime of phi inverse of phi of gamma, which is basically this map. Phi prime of phi inverse. But this phi prime and phi, they are homeomorphism, right? Hence, they are continuous. And so the composition of this thing is continuous. Also, we know this is continuous. And composition of continuous maps are continuous. So that means if this phi after gamma, this is a continuous map. This phi prime after gamma, this is also a continuous map. And then we want to talk about the differentiability of this function, or phi prime of gamma. So now let us consider this phi of gamma. This is differentiable. So can I say phi prime of gamma also differentiable? Why? So for differentiability, I know this one is only continuous, right? Since this one is continuous, this one is differentiable, true. But composition of continuous functions and differentiable functions may be differentiable, but not always. Okay. Okay, so so then we already have a atlas A to the manifold. So this is U alpha of phi alpha. So this is the atlas on the manifold. Now we can always consider the maximal atlas. So if it is a maximal atlas, then all the all the coordinate maps are there. Right. So now we want to consider some special types of these coordinate maps. The maps which are differentiable. Just what do I need to do to consider the only differentiable maps? I just choose which maps are differentiable from this atlas. Because since it is maximal, all the coordinate charts are here, right? So then I need to choose which maps are only differentiable from these continuous maps. And if I choose a different A prime with U alpha phi alpha, but this U alpha and phi alpha, these are now only differentiable. Then I can talk about the differentiability of phi prime after gamma. Now, this phi prime after gamma, I can write it again. Phi prime, phi inverse, phi of gamma. So we know this is differentiable. And since we only choose the differentiable coordinates of function phi alpha, then so this one is now what? This is also differentiable, right? And now you are taking two composition of two differentiable maps. And composition of two differentiable maps are what? Differentiable maps. So that means, although we don't know what is differentiability on the manifold level, but we can always do something like, so if this is my manifold, I can always consider a curve from the real number set to gamma, and I can always consider chart, then to some Rn, then this will be like 5 prime after gamma. But I know the differentiability of this map, which is a map from the real number set to some Rn, right? And what do we require for this map to be differentiable? I need to check the compatibility. If I have another chart map here, 5 prime to some Rn, then I need to check 5 prime after gamma. So if this thing 5 prime after phi inverse, if this is differentiable, then phi prime after gamma is also differentiable. So based on this, we can define the compatible charts. Two charts u comma phi and v comma phi prime are, let's say, star compatible if one u intersection v equals to empty set, and two, if u intersection v is not empty, then the chart transition map maps phi prime after phi inverse from phi of u intersection v to phi prime of u intersection v, and phi inverse after phi prime, sorry, inverse from phi prime of u intersection v to phi of u intersection v are star from the calculus. Although I don't mention what star is, the star can be anything from the calculus. So if I consider only the manifold, the star is just the continuous. So if I consider the star to be C1, C1 is what? It is continuously differentiable maps, right? And star can be C2, star can be C infinity, star can be even C omega, which is the Taylor expandable maps, and even star can be complex differentiable maps or analytic maps. So if these two maps, this one and this one, they are star, we say this this one and this one, they are star compatible. So definition, an atlas is a star compatible atlas if any two charts in A and atlas A are star compatible. Then if I replace the star by C infinity, the atlas will be a C infinity compatible atlas. And if the atlas is C infinity atlas, then we say the manifold is a smooth manifold. That means we can consider differentiability on that manifold. There is a nice theorem and the statement of this theorem is any Ck is greater or equal 1 atlas A of a topological manifold contains a C infinity atlas. Okay, so that means if I have a C1 atlas, then I can always construct a C infinity atlas from that atlas. So I need to check only whether the atlas is C1 or not. So eventually I can always find a C infinity atlas from a C1 atlas. But further, these two are not true. If C1, if an atlas is just a C1 atlas, then you cannot say it is also a C infinity, C omega or complex complex manifold. So now next thing we're going to define is what diffeomorphisms are. So far we know homeomorphism. That means when two topological spaces are homeomorphic, isomorphic in the sense of topology. But what about diffeomorphism? When do we say two manifolds are diffeomorphic to each other? So to consider a diffeomorphism, I have to start with C infinity manifolds, right? So I need to start with M, let's say M and N are C infinity manifolds. M and N are diffeomorphic. Yeah. Yeah. Any maximum sequence. Yeah. Maximum sequence. Okay, so M and N are diffeomorphic if they're existent. It has to be a bijection type of map, right? So I need to find something like F from M to N it has to be bijective. And also, what structure do I require to be this two things, M and N, become diffeomorphic? Yeah, differentiable, but or of which order? C infinity differentiable. So if f from M to N and f inverse from N to M, C infinity, then we say these two manifolds M and N, they are diffeomorphic. But how do I know, or how do I check this f and f prime, they are C infinity? How can I say a function from a manifold f from M to N is C infinity? So I don't know whether this function f is a C infinity map from M to N, but what I know is I have a chart here which is phi, and another chart here which is phi prime. Then this is something like Rn, and this is again something like Rm. But now I can consider this map, and this map is what? It's basically phi inverse of, so this is f of phi prime. So if this is C infinity, then I say the map f is also C infinity. Okay. Yeah. Rn to Rm. I mean, oh, sorry. I should write something like this. Okay. Okay. And check the compatibility, I can consider something like maybe and lambda and lambda prime. Then this is again some Rm, and this is Rm. I need to check this and this. But since we are considering C infinity manifolds, the transition maps are also C infinity. Okay, so this is our discussion on manifold and C infinity manifold. Let us start the idea of, yeah, diffeomorph. Okay, so the first example can be just if you consider Rn to itself, Rn. This the identity map, but you can also consider R to S1 by f of t equals to cosine of t and sine of t. Okay. Now we're going to consider tangent spaces. Okay, so to start the idea of tangent spaces, let us consider this is a manifold M, and there is a point in this manifold P. Now, there may be, I can define a curve that is passing through this point P, and this curve is something like gamma. And we can always consider curves as functions from the set of real numbers to the manifold, right? And so also there is something like this gamma at certain t naught has to be the number p or the point p on the manifold. Now, can I say something about the velocity of this curve? Yeah. Okay. So the velocity. So let us define what velocity mean here. So the velocity of the curve gamma at p is a linear map. And what do we know about linear maps? So it takes an element of a vector space and gives another element of a vector space. So the velocity v of gamma at p is a linear map from C infinity m to the real numbers. What is C infinity m? Infinitely differentiable function on m. So that means if f is an element of C infinity m, then this is a map from m to r. Okay. Then, so basically the idea comes from the vector calculus. So what do we know? What do we know about the directional derivative? Directional derivative of a multivariable function. So yeah, rate of change in a certain direction. So this is something that so back in our head, something the idea is like if f is a function, scalar function, then you take the gradient of this function and you dot it with a vector v. So since this is I, then this is also I, right? So this is the idea of a directional derivative. Now I can interpret this like this. Vi del I, this is an operator acting on the function f, right? And gives you a number because directional derivative is just a number. Okay, so then if I write this kind of a formal way, then it will be something like this: R to M to again R, where R to M is the curve gamma, and this M to R is the function f. Then this is what? F after gamma. And since this is R to R function, I can consider the rate of change of this function. Then d over some dt f after gamma. At a certain point, if I evaluate this, then I get what? Let's say some t naught is equals to v gamma p acting on the function f. Okay. Then we can define the tangent spaces. Tangent space. So tangent space is a set denoted by TPM, and this is just all those velocity vectors, gamma p, gamma smooth curves. Tangent space basically a set or collection of these velocity vectors. Yeah. Now, this tangent space, it is also a vector space. And how do I see that? Maybe we can consider a chart, because if it is a vector space, then I can definitely, and if V gamma p is a vector in TPM, then I can expand the vector in terms of the basis. So V gamma p acting on a function f is equal to, so let us consider a chart u comma x belongs to smooth, definitely, and this gamma is a function from the set of real number to this set u, and for simplicity let us consider gamma of 0 equals to p. Okay, then V gamma p f is basically f of gamma evaluated at 0. This is f of gamma from this, and I'm considering gamma of 0 equals to p, hence I have to evaluate this thing at 0. Now, since I'm considering this chart, then I can f of x inverse of x of gamma, because this x inverse and x, this is just the identity map, prime evaluated at the point 0. And now this is just chain rule, right? Because R to M to R, this is gamma, and X is just this. So, and this is some Rn. Then I can define F. So this is what? This is just X after gamma, and this is X inverse F. So essentially, I am considering now this thing. Right? Okay. Then if I apply the chain rule, this is going to be like X of gamma I prime evaluated at the point 0, then del I f of x inverse at the point x of t. Why? Because x of gamma is what? This gives me R to Rn, right? So I'm considering this map R to Rn, and x of gamma. So the ith component of x of gamma, and I'm evaluating it at the point 0. Then this one is something similar to this, right? And this is f of x inverse evaluated at the point x of p. And for this, I'm considering this. Okay, so for notational simplicity, let us just define something like this. I, also there is a summation on I. So this is x of gamma, this is the ith coordinate. So let us just write it like this. Gamma x I over dt evaluated at the point 0, and this one is del f over del x I. So this is just notation. If we see something like this, then we need to translate it to this. Okay, then I can just consider I d gamma x I over dt at the point 0, and del x I, this whole thing at the point p acting on the function f. Right? But we started with this. Hence, v gamma p is basically summation of I d gamma x I over dt of 0 del over del x I at p. This is the velocity. And this is what? This is something like a number, right? And how many del xi there are there? Yeah, dimension of the manifold. That means, so I can consider these as the basis of the TPM, and these are just the components. So, but it is definitely a chart induced. So let's just, so this del xi at the point p is a chart induced basis. So that means for every point on the manifold, I can always consider a tangent space TPM, and this TPM is so I define TPM, yeah, is a collection of all these velocity vectors. So if this point is P, it is possible there are different curves, and for every curves we know there exists tangent vectors. And these are actually the velocity vectors. And if we consider it in a chart, then this will be the basis of the vector space. So what is the dimension of the TPM? Dimension of the manifold. So dimension of TPM is dimension equal to the dimension of the manifold. Now, let us consider a vector. So, if x belongs to xp belongs to TPM, that means xp is a tangent vector at the point P. Then I can write, so, and at this point, I can have something two different charts. Let's say u comma x and v comma y charts where P belongs to u intersection v. Okay, now I can write xp by some xi in the coordinate system x del xi t. I can also write xi in the y coordinate system del y I t, right? Now, since I'm considering different coordinate system, but this vector xp, it remains invariant, right? There is no change which coordinate system I'm considering. The vector remains invariant. Then, but these two things, xi x and xi y, they are not same. Then, what is the relation between these two components? Or can I see the relation in terms of these two two coordinate system x, y? Okay, so then let us consider del xi. You see this at the point P, and since this is an element of TPM, if I act this thing on a function from the manifold to the real number, then this will be like del I f of x inverse x of t, right? Because I have m to r, but this m is an arbitrary manifold, arbitrary C-infinity manifold. But I also have x, and this is Rn, right? Then this function is what? X inverse composed with m. Then I can differentiate this function now because this is just Rn to R function. And that is what I'm doing here. Okay. Yeah. Okay. So then also I can consider another map y from M to Rn, and this thing is Y inverse of F. Do I need it? No. Okay, so del I F of X inverse XP, but let us just use del I F of Y inverse of Y of X inverse at the point X of P, because I'm considering two different charts, U comma X and V comma Y. Then this gives me so this is a map from Rn to R, and this is a map from Rn to Rn, right? Now this is del I Y of X inverse in the jth component evaluated at the point X of P dotted with del J F of Y inverse at Y of P. Because this one, Y of X inverse, so this is X inverse is basically here to there, and then so I'm considering a point here, and this point is basically X of P because P belongs to the manifold. And then this is F of Y inverse, which is F of Y inverse is this map. That means I need to consider the point here, and that point will be Y of P. But I can translate it to something like this: del Yj over del Xi at the point P, and del over del Yj at the point P on the function f. Yeah. Yeah. Because I'm considering the here. No, we don't. Because this prime is now basically this and this. And using this notation, I can write this. Now I started from del xi at P on the function f, and I got del yj over del xi at the point P, del yj at the point P of f. Now this del over del xi, and this is true for every function f, hence I can write del yj over del xi at the point P del over del yj. Now, what is this? This is the transformation rule for a contravariant tensor, right? of rank 1,0. So I mean, this is not the transformation rule for a contravariant tensor of rank 1,0. This is actually the transformation rule for the component of the contravariant tensor 1,0, because the tensor remains invariant. And that is why this xp is basically in two different coordinate systems they are actually set. But the component, or in different charts, it has a the component of the vector is changing with this expression. Okay, so is there any question so far? Right. I mean, if they are not compatible, then how can I consider this to be in the atlas, where I consider the atlas to be a singularity atlas? It has to be compatible. Any other question? So that means we consider a manifold, then we consider the C infinity structure, C infinity manifold, and finally TPM, the tangent space at the point P. Now, let's say, so let's start with a circle. Okay, so if I consider a tangent space at a point of this circle, then the tangent space will be like what? Okay. Tangent space always, we consider tangent space always at a point. That's why we consider TPM instead of TM, because it is a 3 minutes aligned, right? So if this is the tangent space at that point. So, but if I consider another tangent space here, then this will be something like this. But the tangent space are, so if TPM is a tangent space at the point P and TQM is a tangent space at the point Q, then this is just empty. So it is difficult to draw the picture, but if we consider something like this, let's just put the tangent space like this. Then this is our manifold M, and this is, if this is P, then this is a TPM. This is another TQM. That means I'm attaching all this TPM to every point of the manifold, right? So this gives us a nice construction. And if we collect all these things, like if we take the union of all this TPM, then I get a total space E. And this is actually union of P belongs to M, P Cartesian with TP. Now, if I consider a vector here, so the vector is basically this. And if I take the projection, then I will get the point P here, right? For all these vectors, whatever vector I consider, I will always get the point P if I get the projection. Similarly, for this, I will get this. So for this is P, and for this is Q. So then if I consider E to M, where pi is a projection map and M is the manifold, which is smooth manifold, and E is the total space. Which is also smooth manifold. Then these three pieces of data, E, pi, M, is called a bundle. And this is not just any bundle, this is a special type of bundle which is called the tangent bundle. Bundle for this example. That means if I attach another TPM tangent space to every point of the manifold, then I get a bundle. And this pi map is also a smooth map. Walid, pass me. Okay. So this is a tangent bundle. Now we have E to M, the map pi. I can also go here to there. And this is a map called sigma. And if this map sigma pi is equals to identity map on the manifold, then we say sigma is a section. And if this is a tangent bundle, if E is a tangent bundle, then sigma is vector fields. Why? Because if this is the manifold, then let's say I want to consider the vector fields on this manifold. So a vector field is what? It gives you vector, right? So maybe at this point there is a vector there, and at this point there is a vector in this direction, at this point there is a vector this direction. But at this point we have a TPM, right? So at this point, there is a TPM. At this point, there is another TPM. And at this point, there is another TPM. Now, this is the point P. And if I consider the map sigma, then sigma takes this point to a vector, this, right? And this condition ensures that this sigma will never take you to some vector like this. Because if sigma takes you there, phi, then you get this point, which is not the identity map. Hence, if the sigma satisfies this condition, then we say sigma is a section, and which is a vector field. And finally, I can consider pi inverse of a point P. If I take the pi inverse of the point P, which is actually the pre-image, probably I should pre-image P, then this is what? Pre-image of the point P. A vector or the whole vector space. This whole line is pi, pre-image of pi at the point P, right? So that means this is a fiber. Okay, so basically we attach fiber to each point of the manifold, and then we get the bundle. And this bundle, this is denoted by Tm, and this is called tangent bundle. So what if I consider, so TPM is a vector space, right? And we know there is a co-vector space or dual space of this vector space, TPM, right? What if I attach TP star M instead of TPM for all the points of the manifold? Then that will be, in that case, the sigma will be a section in the cotangent bundle, and that section is called the forms, which is the differential forms. Okay. Okay, thank you very much.